Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I have a course on subsurface machine learning. We've been through a lot on machine learning. As I mentioned before, it's just starting to get really fun right now. We covered in the last lecture the concept of decision tree with the promise that while it's simple and intuitive and not exactly cutting edge, it does provide us an avenue to get into much more, I should say, competitive machine learning or powerful machine learning methodologies. So let's go ahead and talk about the ensemble tree methods. Now, let's do a really quick recap of decision trees, super fast. We'll get into ensemble methods, the motivation for that, Bootstrap, tree bagging, random forest, and we have a hands-on example. Okay, so let's do a little quick review of decision trees. We mentioned in the last lecture the whole idea of a decision tree is to segment the predictor feature space up into a set of regions. The regions are mutually exclusive, they don't overlap, they're exhaustive, there's no gaps, so you can make an estimate across the entire range of all your predictor features. So for every observation within the data set, or for training data, or for testing data, or any use of the model, we'll just simply say we'll take the average of the training data within that region and we'll call that the prediction. Okay, so not a big deal. Now, it's cool because the methodology is based on this idea of hierarchical binary segmentations, and because of that, it can be represented as a decision tree. If we flip that upside down, this would look like a tree where we have a bunch of decisions being applied to a set of thresholds on the predictor features. In this case, we start at one region. We said, okay, porosity is less than 13%. That's region 1. Otherwise, this region here. Then we split that up into region 2, this other group. And then we did our first split on brittleness, resulting in this split right here. So really cool. That's quite intuitive. We can see that now we have a simple tree-based model. I could say, okay, for a combination of for predictor feature values, I could say, okay, follow these rules. If less than greater than each one of the predictor features, I'll arrive at a specific region, and I'll use the average of the region as a prediction model. Now, when do we stop splitting the tree? Well, we could continue and grow the tree until every single training data is in its own region. That would be overfit. Typical approaches apply some type of hyperparameters, like minimum number of training data per region. The idea being that you need so many data to make an estimate of an average. The algorithm will stop when it's reached a point it can't do any more splits without having too few data within the regions. And we talked about some of the limitations of using some threshold or hurdle for reduction in error of the model. And so we go ahead and we build up our tree. We'll build initially a tree that has a reasonable amount of complexity to it. We won't be too concerned about that. And so this right here is the visualization of a complicated tree from R, the example that was worked up in R. And the visualization is really nice. The reason I like it is you can see the branches and the length of the branches are proportional to the decrease in model error in training. So you can see which one of these decisions has the most impact. And you'll see very quickly the first decision has a huge impact. The second one, not so much, maybe on this branch more. And we get out to a point where we're really doing very little to reduce the error in the model. Now, we can also visualize the model as binary hierarchical segmentations of the predictor feature space, porosity, brittleness, and here are all of our cuts that are being made, the thresholds. And we can look at the model and also see, in addition, the estimates are being made within each one of those regions. We've got 12 regions there. Tree may be overgrown. Well, we go ahead and look in k-fold cross-validation that we see, in fact, that as we increase the number of nodes in the tree, we get a continuing decrease in model error in testing the model with a k-fold cross-validation. So we are doing multiple folds of all of the data to do a really nice, robust testing. And we see because the data is actually pretty smooth, the problem isn't that complicated. We're in a situation where we're not seeing overfit even with a pretty complicated tree. And we can make a choice based on the acceptable level of error, or maybe an idea of cost of complexity. I need to have so much reduction in error in order to accept a more complicated tree. So we're going to go through some type of training and testing, and we've just shown a cross-validation approach to do that. Now, if you want more details about decision trees, go back one lecture. And if you want more details about tuning a model of hyperparameters, there's a lecture on hyperparameter tuning that's from a few lectures ago. Let's talk about the ensemble methods. What are we trying to accomplish with ensemble methods? Well, I've shown this figure so many times, you all might be getting kind of bored of it. The expected test mean squared error, this is taken directly from the book James and all, a schematic drawn from one of their figures there. We can expand expected test mean squared error and get three different variance components or error components, and we find that they are additive. And so we've got model variance, which is due to the sensitivity of the model to new training data. It goes up with model complexity. We have model bias, that's error due to the fact the model's not complicated enough to match the complexity of the real phenomenon, and that goes down as you have more complexity. And then you're also going to have the irreducible error. That's just error due to the fact that you don't have enough data. You haven't sampled enough. You haven't sampled the entire range of the predictor features. Maybe you're missing a predictor feature that you could have sampled that would have helped you. And that's independent of model complexity. That's just always there, irreducible error. You sum them all up together and you get the total, the expected test mean squared error right there. Okay, so what's that tell us? It tells us that really at the end of the day, we can improve the expected test mean squared error by reducing the model variance. And in fact, what's interesting is for many models, it's that model variance that's really eating our lunch and reducing our ability to have a very well-behaved model in testing. And so how do we reduce model variance? Well, if you were to just take a set of samples and you wanted to reduce the variance represented in those samples, the best thing you could do is you could do some form of averaging. And so averaging is a very efficient way to reduce variance. Just look at the equation. This is Stats 101 stuff right here. The standard error, the uncertainty in the mean. So the variance of the mean is equal to the variance of sample divided by the number of samples averaged together. And so what's it tell us is that when we average samples together, we're going to reduce the variance. And so we should also acknowledge that this effect is at a maximum reduction that we see here from theory if the individual values are not correlated with each other that we're averaging. If there was a strong degree of correlation, we would not realize this decrease in variance. Okay, so those are important concepts. So what we're going to do is we need to calculate multiple estimates for our prediction problem. Okay, that's the plan. Let's do that. Let's get multiple estimates. This will require multiple prediction models. So we're going to have multiple models. We'll call them estimators. And we're going to have to train multiple models on multiple training data sets. What? Okay, here's the problem. We only have one data set really available to us. We have the response features and we have the predictor features 1 through M. So how are we going to get multiple training data sets to work with? Well, you remember that discussion about Bootstrap a while ago in data prep for uncertainty? There was an evil plan behind that because I knew eventually we'd get here and we'd want to talk about ensemble methods. And so we should talk about Bootstrap. Okay, so what's Bootstrap? This is a recap from before. Bootstrap is a method to assess the uncertainty in a sample statistic by repeated random sampling with replacement. The way I like to say it is that Bootstrap is assessing the uncertainty in a sample statistic from the sample itself, and that's why we think of it as pulling yourself up from your bootstraps. It doesn't seem like it should be possible. Assumptions are a sufficient number of samples, representative sampling, and there's a lot of limitations. It's assuming representative samples. Okay, I just said that. Assume stationarity. Assumes that the data is going to be IID, independent identically distributed. There's not a significant trend in the data and so forth. Only accounts for uncertainty due to too few samples, no uncertainty due to changes away from the data. So if we're using Bootstrap to get uncertainty in some sample statistic, it's not accounting for the things like interpretation, things like spatial context and so forth, and all of the spatial context comes in here. Does not account for the area of interest over which you're making your estimates, assumes the samples are independent of each other, and does not account for other local information sources. This is the non-stationarity issue. Okay, what does Bootstrap look like? I like this figure. If this was the original data set, we had 10 data available to us, we would build a representative CDF. This may include debiasing at this step. We would do 10 Monte Carlo simulations from that CDF, and the result would be a brand new distribution. Why is it a new distribution? Well, there's a chance that you would draw a sample 2 or 3 times maybe, and other samples would not be drawn at all. Or even more times you could draw it. You know what I mean. This is a new realization of the data. Aha, that's exactly what we need. We need multiple realization of data, but for the Bootstrap method of uncertainty and statistic, we'll calculate the statistic of interest right now. Average, P10, kurtosis, skew doesn't matter, but here we just show the average. Okay, repeat. Bootstrap number 2, 10 samples with replacement from the CDF, get a new realization of the data. That's important for us here. Get a realization of the average, put it there. Number 3, and you do that enough times. Something weird happened to my figure here, excuse me. That's getting kind of abstract now. If we do that enough times, we're going to go ahead and get enough samples of the mean, and we can take those and we can then have a distribution uncertainty. But what we're concerned about for ensemble-based methods is we got these realizations of the data, and we're going to use those. Okay, just a couple more comments. Bootstrap approach, back from Efron, 1982. And if you don't believe it, if you think it's weird, it shouldn't work, just prove it to yourself. Run a little Bootstrap in Excel or Python and compare it to the standard error. Do Bootstrap for uncertainty in the mean, and I promise you that standard error will actually work out. As long as the samples were random Monte Carlo simulations, you'll be fine. Now there's advanced versions of Bootstrap, spatial type of approaches, other approaches that try to encode strategy into the sampling, because when you think about it, every time you're doing a Bootstrap sampling, the Monte Carlo sampling, you're simulating the discovery of information. You could put a rule in there that says, if I get a great result, I'm going to keep going. If not, I'm going to bail. I'm going to cut bait and leave. You could do that, and that would be kind of encoding the strategy in, kind of building the game up. That's pretty awesome stuff. Test the strategies out. Okay, this is, once again, just to remind you, one of the most powerful statistical tools ever. It's super awesome, and you could do it in Excel. I have an example of do it in Excel. I have an example of Bootstrap in Python too on my GitHub account if you want to check it out. Okay, so what are we going to do with ensemble-based methods? Because remember, that's what this is all about. We're not bootstrapping for uncertainty and statistic. We're bootstrapping to get multiple realizations of the training data. Okay, apply statistical bootstrap to obtain realizations of the training data. Build a prediction model for each data realization. That's where we're getting our f hat little b. This is going to be a single realization of the training data used to build a model. Now, what do we do? So what we can do now is we can apply all prediction models for each one of the predictions we need to make. So we're going to have multiple estimators now available to us, okay? So for a regression problem, we're going to have, in fact, estimates little b equals 1 through big B estimates. So big B estimates are available to us. And if it's a regression problem, we'll go ahead and just take every one of those estimates and average them. Super easy to do. If it's a classification problem, it's the old adage, just take a majority rule. Take the most likely value from all of those estimates. And so if there are specific discrete classes, you just take the one that's most commonly selected. Okay, so now we have multiple estimators, big B estimators, and we can average them together. And you'll notice this averaging should decrease the model variance. It should attack model variance and make us have a better estimator. That's ensemble-based methods. Okay, so let's go ahead and talk about tree bagging, because that's exactly what tree bagging is. We're going to build an ensemble with multiple bootstrap realizations of the data. The ensemble reduces the model variance as expected, and we can also now, this is super cool, we can overgrow the trees. We can make them too complicated. We can overfit them, and the ensemble approach will actually help us mitigate against overfit. Now, what's also fascinating is that in expectation, when you do Bootstrap, about 1/3 of the data is not used in each tree. Just Bootstrap. If I do Bootstrap on 100 data, in expectation, around 1/3, 33, 34 or so of the data will not be used in every single one of those Bootstrap distributions. It's in expectation. It will vary, of course, and it'll be more close to 1/3 if you have a very large data set to work with. Okay, so what's really cool is that 1/3 that's not used to build the model is now known as out-of-bag samples. They're not actually used to build that model, and so we can actually go ahead and make a prediction with every model for which that data wasn't included at that location. And then we have an ensemble of predictions out of bag that we can then have as a test. So in other words, we can test without doing k-fold cross-validation or just regular cross-validation. The testing's built into the Ensemble method with the out of bag. Super cool. Okay, now one comment I should make is that we want the trees to be decorrelated, diverse from each other, so we maximize the reduction in variance. Remember, if they're highly correlated estimators with each other, we don't get the reduction in variance, and that's going to lead to random forest, but don't worry, we'll cross that bridge when we get there. Okay, so let's go ahead and do tree bagging, the use of Bootstrap to get multiple estimators with trees, and let's go ahead and do it by hand. So I have a data set to work with. I did Bootstrap, and I don't look too carefully at the data set. It's the same in each one of the figures. I didn't pick out the data used in the model, but the models are different from each other. You see how they're different? Check here and here and here. They're all very different because they all use Bootstrap realizations of the data. So there's 6 models here using Bootstrap of the data. Then what I did is I took at every single pixel here, which represents a combination porosity brittleness, that would be a prediction problem. I averaged over these 6 models, and the result is this one right here. So what can we observe about that? That's really interesting. First and foremost, we can observe the fact that we go from having a highly discontinuous type model that as we're averaging, it's becoming a more continuous without any steps in the response over the predictor features. So that's pretty cool. That's interesting. Okay, so this is by hand tree bagging, multiple models from Bootstrap realizations of the data, and then we just average them together at every single combination of predictor features. Now, what is the effect of using more trees and averaging more together? Well, this is an example right here. Tree bagging with one tree, that's just decision tree with a Bootstrap realization of the data. That's all it'll be. Tree bagging where we average over 3 trees, 5 trees, 10 trees, 15 trees, and 30 trees. I hope you can observe that the model is starting to get more smooth, less discontinuous, and in fact we'd find that the model's becoming more stable. Now you can see exactly this smoothing effect because when we were working with just one tree, we have that very discrete, continuous but discrete estimation only over the specific regions of the one tree. So we go to 3, 5, 10, 30 trees, we lose the striations. The actual production, estimated production, we're predicting over much more of a continuous range of production values. Now let's try to observe the reduction in model variance with increasing number of trees. Now, this is very much ocular inspection. I'm not quantifying it here, but I hope you can see it. Here we have multiple models. This is a tree bagging example where we use just one tree, and you can see that they are pretty distinctly different. There's lots of locations where it jumps and changes quite a bit. 5 trees being averaged, 10 trees being averaged. I hope what you can see is that by the time we get to 10 trees, the variability between the models, we're using different Bootstrap sets, is actually starting to decrease. The models are starting to look more like each other. We're seeing a more stable model in the face of changes of the training data. Okay, that's a reduction in model variance as we expected we would see. Okay, now random forest. How do we motivate this? Well, there's a limitation of tree bagging, is that individual trees may be highly correlated with each other. Now, how does this happen? It turns out that if you have a dominant predictor feature, and if you looked at the multiple trees, it's always going to be the first split, or in the second split, and the third split. We saw that with our decision tree before. It was always in porosity until finally it got to brittleness, maybe 3 layers in. So the result is, the trees are going to be quite highly correlated because they're making the same splits. Even if you do Bootstrap resampling of the data, it's still going to be splitting about the same way. The estimators can be very similar. Okay, and so highly correlated trees, there is significantly less reduction in model variance with the ensemble. We're not benefiting as well as we could from the ensemble. The whole premise of random forest is this: take tree bagging, and then for every split, constrain the model so that it can only make a split on a subset of the predictor features. You limit it. Now, a very common way to do this is to use the rule of the square root of m features. If I have 9 predictor features for every one of my splits, I say you can only choose from 3 of the predictor features to find the next best split. Now, when you think about this, it actually results in a worse tree. It's not going to be more accurate. It's not using all of the information. I would say it's a less intelligent estimator. But it forces the trees to evolve in dissimilar manners, and it promotes diversity in the trees. And this is really cool. It actually results in a better result at the end. Okay, so let's go ahead and we'll do it. This is an example of random forest. The previous prediction problem, 300 trees trained to a maximum depth of 3. 1 predictor selected for each split. So we said, nope, you can only pick from 1 predictor feature every split. That way the tree couldn't be always porosity up front. It'd be changing back and forth between the features. Okay, now, did we actually get tree diversity? Well, let's prove it to ourselves. So we made 300 trees where we could only pick 1 predictor feature per split. So of the 300 trees, I took 6 out of there. And then what I did is I stopped the tree and I just looked at the very first split to see where the first split occurred. And when I did that, this is what I saw. A split on brittleness, a split on brittleness, a split on porosity, porosity, brittleness, porosity. And so about half the time, the first split was on brittleness, and half the time the split was on porosity. Now this is increasing greatly the diversity of our trees. In fact, how much has it increased our diversity? Let's do the exact same exercise on tree bagging without forcing ourselves to limit to a subset of the predictor features on the first split. This is what tree bagging would have done. You see that? Every single one of our trees out of our large set is going to make its first split on porosity. And in fact, so the Bootstrap approach is not sufficient to get us diversity. We have to limit it to only consider a subset of the features. Look at this. This is so similar to each other. Most of the time, it's almost the same thing. Okay, so random forest, a simple tweak. We're only considering a subset of the predictor features when we're trying to identify the very next greedy split in building a tree. Let's talk a little bit more about out-of-bags cross-validation or out-of-bag testing for hyperparameter tuning with ensemble methods. So during the construction of our B decision trees in bagging a random forest, every time we build a decision tree, in expectation, we will only use about 2/3 of the data. That's because of the Bootstrap approach. In expectation, 1/3 will be left out. The data not used, that 1/3 in the current model, are known as out-of-bag samples. So what can we do? We can go ahead and we can predict at the out-of-bag sample locations because we haven't used those data. So that's like testing. And so what we can do then is we will have about B divided by 3 predictions at each one of the data locations. And we can go ahead and make an out-of-bag prediction divided by 3 estimates. And so this is just showing this idea that we're taking the B divided by 3 estimates at every location, alpha equals 1 through n data location. And we're making an estimate, an out-of-bag estimate. Now, what we'd expect is sometimes we'll have more or less than B divided by 3 estimates, but in expectation, that's what we should have. Now, what we can then do is at every single location, we have an out-of-bag estimate calculated here, so we can go across all of our 1 through n sample data, our data used to train the model, and we can calculate the out-of-bag mean squared error. Okay, so that's a measure of model goodness that we get during model construction. That's super useful. Now, how does our model perform? How does it work? Well, what I did was I went ahead and I ran our model for the prediction problem of porosity, brittleness to get production in unconventional reservoirs. And I varied in cross-validation using the methodologies that have been just described, going out of bag scores. I worked with variance explained, and I varied the number of trees averaged, in other words, the number of estimators, and the maximum depth, the complexity of the trees. Now here's what's really, really fascinating. The first thing is that what I noticed is as you increase the number of trees averaged, the estimate got better and better and better, and then it just kind of seemed to level off. And what this suggests to me for this example here, that the answer is just have enough estimators. But having too many estimators didn't seem to be a problem. In addition, what we did was we looked at increasing the complexity of the model, and what happens here is if we have a complex enough model, it seems to also level off. Now, I could be concerned once we get to maximum tree depth of like 20 or so, we might be an issue where we're running into other types of hyperparameters that are constraining us, such as the minimum number of data in each region. But in general, this does seem to be quite robust too, that even if we use overly complicated models, it did not seem to get worse. In other words, without a bag testing, the model appears to be quite robust to being overtrained. Okay, so this was a demonstration of Ensemble Methods. We covered the tree bagging and random forest approach. They're very intuitive. Once you understand a decision tree, not so bad to get in. Now, once again, as always, I have a workflow for everything shown here in Python, available in a well-documented example on my GitHub account. You're welcome to walk through that, check it out, edit it, play around with it. It's a lot of fun. All right, so I'm going to go ahead and stop right there. Thank you very much for joining in. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. It is my joy and pleasure and my life's goal to share knowledge of machine learning, data analytics with everybody, the students in my class, even apparently my daughter who just walked by, and also with anybody who's working right now, professionals, engineers, scientists, and so forth. Come on in, join in, participate in the class. All right, so I hope this was helpful to you. Take care.